Hello. Hello and welcome to this video on exemplified read-through of text functions and operators. Now, I know things are boring when we do read-through, but I have an example here which will help you understand. And if you look at this, it is roughly 3,000 lines of script. So it will be a big example. Now, the thing about text search functions is that it helps you do search on Postgres data type. In past, for example, personally me as well used to use something like Elasticsearch. For example, when I did my QA way back in 2013, 13 years ago, I did search through Elasticsearch, but now text search functions and full text search capabilities of Postgres allows you to mimic most of the functionality provided by something like Elasticsearch or Apache Solr. You don't need a separate search engine and you don't need to give extra resources to the search engine. You can do the text search right inside the PostgreSQL. So this we will probably do tomorrow, and for today, I believe we can finish this text search functions and operators today. So it is important that you have watched the section 8.11 video when we did it. You should know what is a TS vector, what is a TS query. Those types, if you don't understand, you can go in my playlist and watch those videos. So we build upon the knowledge we have acquired earlier. So we will read through the operators and functions, and then tomorrow we will look at the example. So let's start the read through. Table 9.42, 43, and 44 summarize the functions and operators that are provided for full text searching. See Chapter 12 for a detailed explanation of PostgreSQL's text search facility. Now, this video is going to be very important. Particularly, we will cover Chapter 12 later on. So a lot of people know how to write queries, but very few people actually implement something like a search engine using the SPS facility of PostgreSQL. So pay attention and you'll be benefited by a huge utility of knowledge. So first operator is @ @. So it applies on PS vector and PS query, and it returns a boolean. So does TS vector match TS query? The arguments can be given in either order. So to TS vector, fat cats ate rats, and to TS query is cat and rat, and it is true. So TS vector matches the TS query. Then we have text @ TS query. So we give a piece of text string, and it implicitly invokes to TS vector, and then runs the TS query match. Then we have TS vector pipe TS vector, double pipe actually, concatenates two TS vectors if both inputs contain let's see positions. The second input's positions are adjusted accordingly. So we have A:1, B:2 PS vector, then C1, D2, D3, and is combined to A:1, B:2, 5, and C:3, D:4. Then we have TS query and TS query, and two TS queries together, producing a query that matches documents that match both input queries. So we have fat or rat TS query and then cat TS query, and it becomes fat or rat and cat. Then we have OR operator for TS query, which ORs two TS queries together, producing a query that matches document that match other input query. So it is much like AND gate and this is much like OR gate. Then we have not TS query. negates a TS query, producing a query that matches document that do not match the input query. Then we have TS query less than minus greater than constructs a phrase query which matches if the two input queries match at successive lexemes. Then we have TS query at the rate greater than TS query. Does first TS query contain the second? Let's consider only whether all the lexemes appearing in one TS query appear in the other, ignoring the combining operators. So cat TS query, does it contain the second cat and that? So that is not true. Then we have TS query less than and at the rate. Is first TS query containing second? So cat here is containing cat and that, and cat is also containing not cat and that. In addition to these specialized operators, the usual composition operators shown in table 9.1 are available for two types, TS vector and TS query. These are not very useful for text searching, but allow, for example, unique indexes to be built on column of these types. Then we have text search functions. Array to vector takes an array of text and gives a TS vector. Converts an array of text string to a TS vector. The given strings are used as lexemes as is without further processing. Array elements must not be empty strings or null. So we have an array fat cat rat, and it is converted to, it is parted to a text array, and it gives us cat fat cat. Get current TS config returns the OID of the current default text search configuration. So here it is English. Then we have length, takes an argument TS vector, returning an integer. It returns the number of lexemes in the TS vector. So here we have three lexemes, start, cat, and that. So the length is 3. Then we have num node, which returns the number of lexemes plus operators in the TS query. So here we see 3 lexemes, start, rat, and cat, and 2 operators, ampersand and or pipe. So total is 5. Plain to TS query takes a config and optional config and query text. Converts text to a TS query, normalizing words according to the specified or default configuration. Any punctuation in the string is ignored. It doesn't determine query operators. The resulting query matches documents containing all non-stop words in the text. So we have plain to TS query and configuration is English, the fat rat. So the lexemes which we get here is fat and that. Phrase to TS query, just like previous one, converts text to a TS query, normalizing words according to the specified or default configuration. Any punctuation is ignored and so on. So we have phrase to TS query, the fat cats, and it produces this TS query. And phrase to TS query English, the cat and rats produces another TS query. Then we have web search to TS query, converts text to a TS query, normalizing words according to the specified or default configuration. Quoted word sequences are converted to phrase texts. The word or is understood as producing an or operator, and the dash produces a not operator. Other punctuation is ignored. This approximates the behavior of some common web search tools. So we have English within double quotes pattern that or fact dog. So this produces this TS query. Then we have query tree, which takes a TS query and outputs text, produces a representation of an indexable portion of a TS query. A result that is empty or just T indicates a non-indexable query. Then we have set weight, takes a TS vector argument and weight. So assigns the specific weight to each element of the vector. So we have this cat with weight 2 and 4, cat with the weight 3, rat with 5D. So these weights are assigned to the TS vector. Then we have set weight, which takes the weight and then it also takes lexemes as a text array. So the strings in lexemes are taken as lexemes array without further processing. Strings that do not match any lexeme in vector are ignored. So we have fat, cat, rat as PS vector, and then we have lexeme as A and cat, rat. So cat is assigned a weight of 3A, fat is assigned a weight of 2 and 4, and rat is assigned a weight of 5 and 6. When we have stripped, removes positions and weights from the TS vector argument. So this is the weight and position, and those are removed. Then we have two TS query, which takes a text and converts it into query, converts text to a TS query, normalizing words according to specified or default configuration. The words must be combined by valid TS query operators. Then we have two TS vector. Again, it takes a document this time and produces a TS vector, converts text to a TS vector, normalizing words and so on. Position information is included in the result. So we have fat, and this is that. So fat occurs at second position, that occurs at third position. Then we have two TS vector, which can take JSON or JSONB and outputs TS vector. So converts each string value in the JSON document to a TS vector, normalizing words uses specified or default configuration. The results are then concatenated in document order to produce the output. Position information is generated as though one stop word exists between each pair of string values. Here, that document order of the field of a JSON object is implementation dependent. When the input is JSONB, observe the difference in the examples. So we have A, P, and value is the factors. Then B is dog, which is JSON. The position of dog is 5, and fat is 2, and that is 3. And then we have the same for JSONB. Now dog is 1, fat is 4, and rat is 5. So you see that the ordering in JSONB is not preserved. That we have already understood because JSONB is optimized when the data is stored. Then we have JSON to TS vector, like previous one, takes a JSON argument and a JSONB filter. In both cases, filter is in JSONB. Selects each item in the JSON document that is requested by the filter and converts each one to a TS vector, normalizing words according to the specified or default configuration. The results are then concatenated in document order to produce the output. So it's a similar thing. The filter must be a JSONB array containing 0 or more of these keywords, string to include all string values, numeric to include all numeric values, boolean for booleans, all for to include all the above. As a special case, the filter can also be simple JSON value, that is one of these keywords. So here our filter is string and numeric. So we get 1, 2, 3 at position 5 and 5 at position 2. Then we have filter all, so we get everything in the output. Then we have 2 underscore delete, takes TS vector argument and text lexeme and outputs a TS vector. Removes any occurrence of the given lexeme and from the vector. The lexeme string is treated as a lexeme array without further processing. So we have this TS vector and we are deleting fat. So if we delete fat, we are left with cat and rat. Then we have TS underscore delete. Lexeme is again text and vector is TS vector. Removes any occurrence of the lexemes in lexemes from the vector. So the only difference is that this takes a single text argument, this takes an array, and all will be deleted. Then we have 2 underscore filter, which takes a TS vector and weights character array. So selects only elements with the given weights from the vector. So here weights are AD. So if you look at this, then B is cat 3B and that is 5A. Sorry, there is no small a actually. Okay, and B is small, 3B is here. So if you see this, then the filters are applied and fact is removed. Cat 3b is preserved because we have B here, and that 5a is preserved because A is there, and 7c is removed. Then we have two headline, which takes a config argument, document as a text, PS query, and options as text. It displays in an abbreviated form the message for the query in the document, which must be raw text, not a PS vector. Words in the document are normalized according to the specified or default configuration before matching the query. Use of this function is discussed in section 12. It also describes the available options. So we have the text here, the fact that is there, and then we have our query, which is cat. So now we see that cat is in bold here. Then we have PS underscore headline. So in both the cases, once it takes JSON, then it takes JSON-B. So displays in an abbreviated form matches for the query that occur in the string values within the JSON document. So a lot of it refers to chapter 12. Okay. So what I will do is I will rather skip this part and okay, I think we can cover this. Okay, so TS headline is like that, similar to this TS headline. Then we move on to TS underscore rank, which takes weights, optional, vector TS vector, and query TS query, and normalization is an integer. Computes a score showing how well the vector matches the query. Then we have TS underscore rank underscore CD. So computes a score showing how well the vector matches the query using a cover density algorithm. Again, we are asked to see chapter 12. So TS underscore rank underscore CD, when search for cat, then our score is 0.1 here. TS underscore rewrite takes a query, takes a target, takes a substitute. So all are of type TS query. Replaces occurrences of target with substitute within the query. So we have a TS query A and B, and our target is A, and substitute is foo bar. So it becomes B and foo bar. Then we have TS underscore rewrite. We have a query of type TS query and selected of type text. Replaces portion of the query according to targets and substitutes obtained by executing a select command. So we have select T, S from aliases. So without the aliases table, it is rather difficult to justify. But you understand that A is now replaced by foo bar. You'll see this in chapter 12. Then we have TS query phrase, which takes two TS query arguments, query 1 and query 2, constructs a phrase query that searches for matches of query 1 and query 2 at successive lexeme, same as less than minus greater than operator. So it does that, and then we have TS query phrase, which takes two query arguments and the distance as an integer, constructs a phrase query that searches for matches of query 1 and query 2 that occur exactly distance lexeme apart. So here we have fat and cat, and the distance is 10, so it creates that, searches for that. TS vector to array, so it converts a TS vector to an array of lexemes. So fat, cat were the words, so it created the array. Then we have unmatched, it takes TS vector and produces set of records. So takes a lexeme, output will contain lexeme, positions, and weight. So we have self star from unmatched, and this is our TS vector argument, and we have cat as a position, not at 3 position, it has 3 positions. Then we have weight at D, fat is at positions 2 and 4, and weights are DD, and that is 5 and 8. All the text search functions that accept an optional edge config arguments will use the configuration specified by default text search config when that argument is omitted. The functions in table 9.44 are listed separately because they are not usually used in everyday text searching operation. They are primarily helpful for development and debugging of new text search configuration. So first is that ts underscore debug takes the config and document text and outputs, set of record, alias, description, token, dictionaries, and dictionary along with lexeme. Extracts and normalizes token from the document according to a specified or default text search configuration and returns information about how each token was processed. So the bracket supernovas is a document in English, and here is the output. So alias is like ASCII word. Our description is word or ASCII. Then we have keywords and so on. Then we have ts underscore lex size takes an we cover this? I don't care about it because I cannot help you with developing new config. The reason is that the only language I know of use is English. I don't know any other languages. So I really can't help you with development of a new text search configuration. English is the only language I know. So it is best that we skip these. Okay, there are examples. I will cover these. Okay, so we will cover this in the next video, and we will look at the example also. Text search debugging functions we will cover in the next video. So I'll end this video here, and I hope that you are finding these videos useful, particularly this one. And in the next video tomorrow, we will go through the remainder of rather full of table 9.44, and through the example I have shown you, which we will use to understand more about full text search of PostgreSQL. So thanks a lot for watching the video, and I'll see you in the next one tomorrow with the examples and all. So keep learning and have a nice day. Enjoy.